Hi, this is the next video for the chapter 3 of the series. So in the last video I talked to you about sequences in general and how we could use recurrence relations to show how to get from one term to the next. In this video and the subsequent videos following this, I'm going to be looking at specifically arithmetic sequences. Now, an arithmetic sequence is just another word for a linear sequence. So you are already familiar with sequences like this that are going up by the same amount each time. This would be a linear sequence that you've already known about. We generally call them arithmetic sequences, and there's a whole section about arithmetic sequences. There's much more that we can do with them rather than just working out the nth term. So the next set of videos is all about, in particular, these types of sequences, arithmetic sequences. So, using our recurrence relation notation, an arithmetic sequence is something of this form where each term is the previous term plus or minus, if this is negative, some constant. Now we use the letter D, and that stands for the common difference. So the common difference is the number by which we add or subtract to get from one term to the next. So in this one here, each term is the previous term plus 3. So if we start off with a 5, to get the next term we need to add 3. To get the next term we need to add 3. We need to add 3, and so on. This one here starts off at -1. Then to get the next term we need to add 5, we need to add 5, we need to add 5, and so on. And this one here starts off at 23. To get the next term we need to do each term take 2. So take 2, take 2, take 2, and so on. I've just put some little dots on. This suggests that that sequence will go on and on forever. So that is how we write infinite sequences. So if there are some little dots, then that suggests that that sequence can carry on and on forever with infinitely many terms. Now these should be familiar, ones that you're used to. For these, not only can we describe how to get from one term to the next, but you also know how we can write the nth term. You've been doing this at high school. So the nth term, un, will be, because it's going up by 3, that's 3n plus 2. Okay? If you're unsure about how to get this, just go back a place. Whatever number goes there will be there. Okay, this, remember, links the position that the number's in with its term. So this is in position 1, so U1 will be 3 times 1 plus 2 is 5. This is in position 2, U2 will be 3 times 2 plus 2 is 8, and so on. So this tells us how to get from one term to the next. This tells us how to get from the position that the number is in to the value. This one here is going up by 5 each time, so that's going to be 5n, and if we go back a place, we'll get to -6. And then this one here is going down by 2 each time, and then if we go back a place, we'll get to 25. Okay, so each of these arithmetic sequences, we can work out its own nth term. We can also go the other way. If we know the nth term, we can write down what the recurrence relation is. This one here, if we write down the first few terms of the sequence, when n is 1, u1 will be 4 times 1 plus 1, which is 5. u2 will be 4 times 2 plus 1, which is 9. u3 will be 4 times 3 plus 1, which is 13. So you can see it's going up by 4 each time. So if we wanted to write down the recurrence relation, it's going to be un plus 1 equals un plus 4, where the first term is 5. This next one, u1, will be 3 minus 2 times 1, which is 1. When n is 2, 3 minus 2 times 2, that's 4, so 3 take 4 is minus 1. When n is 3, u3, 3 take 2 times 3, well that's 6, so 3 take 6 is minus 3, and so on. So it's starting with 1 and it's taking 2 off each time. So un plus 1 will be un take 2, where the first term is 1. And then this last one, first term, u1, 5 times 1 take 2 is 3. u2, 5 times 2 take 2 is 8. u3, 5 times 3 take 2 is 13. So you can see it's going up by 5 each time. So un plus 1 equals un plus 5, where the first term is 3. Okay, so we can bounce from the recurrence relation, the term-to-term rule, to the nth term, and then back again via the sequence. Okay, so when you're using these, it's always useful to be able to see the sequence, and then you know what you're playing with. Now all these arithmetic sequences have things in common which we're going to look at. We've also mentioned in the title arithmetic series. The difference between a sequence and a series is just the fact that a series is the sum of terms in a sequence. So an arithmetic series is the sum of the terms of an arithmetic sequence. So here's your sequence. There's the first 6 terms of the sequence. There's little commas in between to denote it's just a sequence of numbers. The series is each of these numbers added up. Okay, now you're going to be expected to be able to work out the sum of terms of an arithmetic series, and you might have to work out, for example, the sum of the first 200 terms of a series. Now what you don't want to have to do is add them all up individually, so there's going to have to be a way where we can do that quickly, and there is. And the reason why that there's a way we can do that is because all these arithmetic series have things in common. Because they have lots of things in common, it means we can generalize an nth term for any particular sequence. So where these nth terms are valid for these particular sequences, what we want to do is to be able to generalize and get a general nth term for any sequence. And to do that, we use A and D notation. So just consider this series 2, 5, 8, 11, 14, 17, and so on. So you can see that this is going up by 3 each time. So D which is the common difference, as I mentioned before, D equals 3. A, well, we use A to represent the first term. And A in this case is 2. Okay, so this is just using A just for arithmetic sequences and series. I'm not going to use it for any old sequence, just for arithmetic. So this 2, this is A. To get from here to here, in this case, we need to add on the 3. So this 5 is 2 plus 3. So it's A plus D. The 8, well, that's 2 plus 3, which is the 5, plus another 3. So that's A plus 2D. And this is A plus 3D, and so on. Okay? Now this is in position 1, so that's U1. This is in U2. This is in position 3. This is in position 4, and so on. So if you look here, the number of D's is 1 less than the position. So this is where n is 1, this is where n is 2, this is where n is 3, and so on. So this number here is always 1 less than the position it's in. That means that there will be some term in position n. So in other words, the nth term, that's going to be the first term plus how many D's? Well, it's however many, whatever n is, take 1. So n is n. So it's going to be n take 1 lots of D. And that is going to be our nth term. So un is A plus n minus 1 D. That is the nth term for any arithmetic sequence. Okay, because I could have picked any numbers there, it wouldn't have made any difference. If I'd have picked 4, 9, 14, 19, it wouldn't have made any difference. A would have been 4, D would have been 5, this would have been A, this would have been A plus D, this would have been A plus D, and so on. So it doesn't matter what this is, as long as it is an arithmetic sequence, then these are always going to be the same. So by generalizing it in terms of its first term and its common difference, we can now find a general nth term for any series. Okay, and you can still use this now. If I say A is 2 and D is 3, then UN is 2 plus n minus 1 times 3. 2 plus, if I just expand that out, 3n minus 3, so UN equals 3n minus 1. And that is the specific nth term for that sequence. Okay, but that is our general nth term for any arithmetic sequence. And you've got to remember that. Now we can use that, because we know this, we can use that now to solve problems involving arithmetic sequences. Before we do that, let's just work out some nth terms for this. Okay, so I know you could probably work it out old school, but we're going to use A and D. So here, A is 4 and D is 3. So UN is going to be A plus N minus 1 D. So 4 plus 3n minus 3, which means UN is 3n plus 1. Okay, that is the nth term. So that's our nth term for that particular sequence. And then we can get U20 by substituting 20 in here. So 3 times 20 plus 1 is 61. And that's the 20th term. Okay, I would like you to just pause the video and just have a little go at the next two. Try and do it in the same way that I've just done it. Okay, so the nth term will be 5n plus 2, and then the 20th term will be 5 times 20 plus 2, which is 102. And then for this one, UN will be minus 4n plus 16, and U20 will be minus 4 times 20 plus 16, which is minus 64. So hopefully you got those. Now then, find the number of terms in each of the arithmetic series. So you can see that there's no dots, which means that that is the last term. So this is a finite series, okay, because it's come to an end. Find the number of terms in each of the arithmetic series. Well, that's the first term. That's the second term, that's the third term, that's in unknown value of n's term. So what we want to do is work out the nth term and then solve. Because by working out, if we solve and put our nth term equal to 121, then that will tell us the position that that is in. And because that's the last number in the series, then that must be how many terms there are. So I hope that makes sense. So A is 5, D is 4, so UN equals A plus N minus 1 D. So UN equals 5 plus 4n minus 4, UN equals 4n minus 1, plus 1, sorry. Okay, so that is the nth term. There will be some value of n that when you substitute it into here, you get 121. So if we solve, 4n equals 120, n equals 30. That's in position 30, and because that's the last number in that series, then there must be 30 terms in that series. So I hope that makes sense. Okay, so just have a little go at the second one. Pause the video. Okay, so this one, the nth term is 3n minus 7, and 89 is the last number, so 3n minus 7 equals 89, 3n equals 96, so n equals 32. So there must be 32 terms in that series. Okay, here's some problems now that we can use this A and D notation for. So remember, we've got un, that's our nth term. That's what we're going to use. The third term of an arithmetic series is 30, and the 10th term is 9. Find A and D. Okay, so we know that the third term is 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The third term is 30, and the 10th term is 9. Okay. What we don't want to do is start guessing and trying to figure out gaps. We're going to use our A and D notation. The third term is going to be A plus 2D. So when n is 3, the third term, this is going to be 2. So you know that A plus 2D is 30. So go straight to A and D notation. So the third term is going to be A plus 2D. The 10th term, that's going to be A plus 9D equals 9. Okay, and you can see we've got simultaneous equations, we've got two unknowns, simultaneous equations. So if I take 2D, take 9D is minus 7D, 30 take 9 is 21, divide by 7, D is minus 3. And if D is minus 3, we'll whack that in here, 2 times minus 3 is minus 6, plus the 30, so A minus 6 equals 30, which means A must be 36. Okay, which makes sense. 36, take off 3 is 33, 30, 27, and so on. Okay, so when you are told positions that our numbers are in an arithmetic series, then use A and D notation and solve. The 20th term of an arithmetic series is 14, and the 40th is minus 6. Find the 10th. Okay, now to find the 10th, we're going to need to know what A and D are. So we've got two pieces of information to work out A and D. So the 20th term, A plus 19D, that's the 20th term, is 14. And A plus 39D, that's the 40th term, is minus 6. Simultaneous equations again, so we take negative 20D equals 20, which means D is minus 1. And if you pop that in here, that's minus 19. So A equals 14 plus 19, which means A is 33. So now we know that. We can find the 10th term. So U10, the 10th term, is denoted by A plus 9D. So if we say A plus 9D, sorry, we put some numbers in. The 10th term is going to be 33 plus minus 9. So U10 is going to be 24, and that's the 10th term. Okay, so use the information that you've been given to form an equation for A and D, and then use that equation or that information then to work out the 10th term. Oops. Okay, this one's slightly different. The first 3 terms of an arithmetic series are 5x minus 3, 2x plus 6, and x plus 5. Find the value of x and hence the value of the first 3 terms. And it says, hint, form an equation in terms of x using, that should say, the common difference. Okay, so this is a little bit different because we've got unknowns in the terms. Now, when you've got ones like this, what you know sort of goes back to the recurrence relation. If each term is the previous term plus D, then D is each term minus the previous term. So that the second term minus the first term is the common difference. That's going up by D. And the third term minus the second term is also the common difference. Now we can use that to form an equation using the common difference, because we can say that the third term take the second term, if that's the common difference, and the second term take the first term is the common difference, then those two must be equal to each other, because they are both the common difference. So U3, x plus 5, take the second term, so just use brackets, because it's take all of that. That's equal to the second term, take the first term. Let's expand. X plus 5, take 2x, take 6, is 2x plus 6 minus 5x plus 3. So minus x minus 1 equals minus 3x plus 9. I'll move that over there. I'll move the minus 1 over there, which means x equals 5. And then it says, so find the value of x and hence the value of the first 3 terms. Well, if x equals 5, 5 times 5 take 3 is 22. 2 times 5 plus 6 is 16. And 5 plus 5 is 10. And you can see that you've got a sequence that's going down by 6 each time. So just check. Obviously, if that wasn't an arithmetic sequence, you know you've gone wrong somewhere. Right, I would like to have a go at questions 4 to 10 on exercise 3A. So those questions are very similar to the ones I have just been through. So have a go at them.